one point of information is that there will be one more lecture in the course next week. Um, uh, um, a problem set will be distributed in a few days, probably before the next lecture. I will make up some problems and send them over to Nikolai, and he can send them to the group, or maybe, yeah, probably. And I'll try to do that in a few days so that you may have some questions about the problems next week. You can ask me. We may continue in January in some form. We'll see. That's a matter of planning, and it won't be a formal course, I don't think, but I could continue talking about covariant homology in relation to virtual knots, and thought that it might be a good idea. So we'll keep you posted. I think those are the main points. So today, I'm going to talk about a number of things. The first thing I want to talk about is the tubing relation. So you will recall how that worked, right? You have bits of surface one, two, 3, and 4, and you put tubes from 1 to 2, minus from 2 to 3, plus from 3 to 4, and minus from 1 to 4 tubes. So this is surface, and these are tubes. And you assert that this is equal to 0. And we had examples of that before. So for example, you might have some situation like this where there's a tube between two surfaces here. Right, and then these two surfaces are left alone, and then you would have this surface, and there would be a tube from this surface to this surface, and this one would be left alone, and then plus, and so on, and it would all be equal to 0. And the result is that that cobordisms modulo the tube relation forms the correct background for the covariant homology. And we explained in quite a bit of detail last time how that works. So I got to thinking during the week, well, this looks something like a cocycle kind of relation, some sort of cohomological relation. So why not explore what sort of a relation it would be if you think of it that way? And let's just talk about that. Um, what I have so far is not quite yet going anywhere, but I think it's interesting, so I felt like talking about it for a few minutes. So let's look at that. Oop. So so how would this look? This would look like the following. Um, I could define a boundary of a quadruple A, B, C, D, and those would be the surfaces in our case, but I'm looking at the abstract formalism of it, and that's going to be equal to triplets. A is connected to B, and C and D are left alone, minus A with B and C connected, and D is left alone, plus A and B and C and D are connected. So I make them into one object, one surface object. So started with 4 surface objects, we have 3 surface objects, and then am I keeping track of my signs? Plus, minus. And then the last one we have D and A are connected to one another, right? And if this were a boundary map, then would it be a boundary map in some homological system? Would there be a chain complex? Would boundary equal to 0? What would boundary equal to 0 mean in such a situation? Well, one way to think about this would be to regard this as a product, all right? So just to make it into something more algebraic, if I regard it as a product, then it would look like this. The boundary of A, B, C, D would be equal to AB, the product. This would be a product. Comma C, D, minus A, and then B and C would be put together, D, and then plus A and B and C and D would be put together, and then minus D and A. I'll just run it around multiplying cyclically like that, B and C, okay? We're thinking of taking it cyclically like that. And then you can ask what is needed for boundary composed with boundary to be equal to 0. And this is actually an interesting case in this kind of formal homological boundary situation. Let's do the exercise and see what happens if we take the boundary of the boundary. Maybe we need a new board. So we want to take the boundary of A, B, C, and D. So let me go ahead and do it. So I get the boundary of, and I'll do this all over again, sorry, quickly though. A, B, C, D, minus A, B, C, D, plus A, B, C, D, minus DA, B, and C. Okay. And now I want to take the boundary of that again. I'll use the same rule, of course. So I then have, for the first one, I have AB times C. Nobody said the multiplication was associative or anything, just a binary operation. ABC, then D, that's the first one, gives me 2 rather than 3, then minus AB, CD, and then plus D, AB, C. The next one, minus A times BC, comma D, plus A, BC, D, and minus DA, BC. And lastly, plus AB, CD, minus DA, B. I'm sorry. I was working on the third one and I stopped in the middle. Okay. A, B, C, D, minus A, B, C, D, and plus CD times A and B. Right. And then the last one I'll put down here, minus DA, B, C, plus DA, BC, and minus C, DA, B. And then you see, if you look at this, I hope, that it's equal to 0 exactly when the operation AB is associative and commutative the way we wrote it. Now maybe I don't need commutativity if I hadn't cyclically run it that way and written ABD. Let's look at that. Probably I should have just defined this to be AD and then I wouldn't need commutativity, but let's look at it and see. Certainly associativity. Watch. ABCD. It's canceled by somebody. Right there. ABCD. ABCD. ABCD canceled. Let's just docket it. Okay. ABCD is canceled by that. ABCD is canceled by this. ABCD is canceled right here. If this were ABD, well, let's see what happened. DAB. Let's keep going. DABC, that's fine. Okay. And there it is, DAB and DAB. So that's all right too. That one worked. And CDA and CDA. So I didn't need commutativity if I defined things the way I did by cyclically multiplying around the bend. I just need associativity. Okay. This is what I discovered, and then I knew that this was not an unknown result, that boundary operators of this kind, which are related to group homology, are going to have boundary equal to 0 if the algebra is associative. So this is what happens. So you see, what is associative in our situation? Let's take a look at that now and see whether we can formulate further. So we go back to our situation and ask, well, what was happening? We had a bit of surface and another bit of surface, and you attached one to the other. That was the operation. And then you attached another bit of surface to that by another tube, like that. And that was doing it one way. And then this would be like A, B, and then C, right? Whereas A, B, C would be putting these two tubes together and running that one in. But indeed, it is true that that in terms of cobordisms of surfaces, we have associativity. Associativity would mean that if I connected the tubes here first, and then I connected that to a tube over here, this would be A, B, C, and so these are the same. So so if we're thinking in terms of the tube connections, then we already do have the associativity, and so we can think of these boundary operators as operating on on cobordisms. On the other hand, the way I am looking at it geometrically by saying take 4 bits of surface or 3 bits of surface and put tubes between them is very free and not quite algebraically defined. So, so what we're seeing is that the tube relation looks like setting boundary alpha equal to 0 in a complex made from cobordisms, so that the cobordisms generate the complex, but at this stage, the boundary map is not quite algebraically defined. Nevertheless, it looks like obtaining tube relation is like taking cobordisms modulo boundary of cobordisms in some sense. So it looks like one is doing some sort of homology to obtain the right collection of cobordisms. I think it's interesting and suggestive, and so the question then is simply what will come of further thought along this line. I think it's worth thinking about, and I'm going to continue thinking about it. If we do to have some more talks about Kauffman homology and knots and virtual knots, I probably will have formulated this more precisely by that time. But I think that it's good to just think of some way of asking questions about how did it come about that this four-tube relation ends up being just what you need in order to have topological invariance for the Kauffman homology, in order to have chain homotopy invariance for it. It's really important in understanding what's going on with Kauffman homology, in my opinion. I think also that there is an analogy here that's worth telling you about. You may not have seen it. And it's one that might have been in the back of Dror's mind. So let me tell you about that too. The 4-2 tube relation is somehow analogous to the famous four-term relation for Vasiliev invariance of knots. Now, in order to tell you about that, I want to tell you what is the four-term relation so that you too can think about this. You can think about that analogy as well. And this is something which is really interesting, but it will take us a few minutes to set up the background for this. So I'm going to take a little time and do that to show you what this is. An invariant of knots, not necessarily virtual knots, but we can do it for virtual knots as well, or links, is said to be a Vasiliev invariant. Let's call our invariant I. If I applied to a diagram with a positive crossing minus I applied to a diagram with a negative crossing is equal to I applied to a diagram with a singular crossing. That is, the invariant is defined on, I'll just write knots, and that means knots and links, on knots with singular crossings. So, for example, you could talk about the invariant of a trefoil knot with a singular crossing. Now, we've already met some singular crossings when we talked about the Montour bracket, and we could generalize virtual knot theory to include singular crossings. But singular crossings, these are graphical, not virtual. And the best way to tell you what I mean by a singular crossing is probably to tell you the extra moves. The extra moves are, well, one extra move of importance is that if you were going under and under like that, why then this would be equivalent to going here like that. something you're not allowed to do in virtual knot theory. You can't pass classical crossings past virtual crossings. And this could be under or over. So I should draw the other one just for the sake of completeness here. And of course, all other orientations can be used as well. So it can go over like that. Okay, so that's one thing you're allowed to do. You're allowed to if you have so this is just as though it were an embedded graph, right? So we're really talking about embedded graphs embedded in R3. So this is much more direct kind of an idea than the virtual idea. And then these vertices are going to be rigid, not topological, and I have to show you that on the next slide. We're out of room here. So what I mean by that is the following. Suppose you wanted to get rid of something that was like this. Have I got that the way I want? Nope. Yeah. Okay. So that means the endpoints are fixed. And what you did was you grabbed it in the middle and turned it around. It's a rigid vertex. When you isotope it, you have to turn it as though a rigid vertex. So what you can do is you can turn it rigidly, and then the cyclic order of edges that go in just flips over. But so if this is number 1 and this is number 2 and this is number 3 and this is number 4, then you see up here you have 1, 4, 3, 2. So you're allowed to take that like a little puck, a little round flat disc, and pick it up and turn it around by 180 degrees and put it back in the plane. And it changes the cyclic order from 1, 2, 3, 4 clockwise to 1, 2, 3, 4 counterclockwise. The strings go along with it. And that's the rigidity of the vertex. So we assume that, and we assume the other extra move. We will not, this will not cancel. This won't cancel. So that's what I call rigid vertex moves. Okay, what we just described above. All right. And so here's a nice fact. We're digressing a little bit into the theory of these so that I can show you the 4-term relation. The nice fact is that if J, if J of J sub k is an invariant of knots and links, then we can extend J to RV graphs, rigid vertex graphs, via, if ever you see a vertex, then you're just going to replace it by maybe an over and an under. You can do it in many ways, but let me show it to you for this. We'll replace it by an over vertex with an a variable a, and another variable b for the under vertex, and expand in this way and evaluate j on the knots and links. And this extension, j extended, is an RBG invariant. So that's what I have to convince you of. This means that if I start with an ordinary invariant of knots and links, I can get a Vassiliev invariant by just writing this as a is 1 and b is -1. But then we'll see that that's only the beginning of the story. But let me show you that this really does extend to give us an invariant. So for example, we could let jk of q be equal to the Jones polynomial. But it could be anything, okay? And then we want to see what would happen if we looked at j of something like this, a node and somebody like that, right? And we want to see that what will happen. Well, by definition, this is going to be a times j of, and I have to draw this diagram again, over. Plus b times j of the diagram drawn with the flipped crossing, right? That was my definition. I'm going to insert positive and negative crossings with a and b weight. Oh, but j is an invariant, so that says that this is equal to a j of, and it's an invariant of knots and links. So after we have, lots of different knots and links that could fall in there, but in every case it's an invariant, so this can come down, and j can come down on the other one as well. And now you see the whole idea, don't you? Right? Because now this is equal to, by definition, j of our thing with the thing below. So that's all there is to it. You see, it's tautological that it's invariant under the moves, because when you replace this with a tangle, in this case a very simple tangle, a plus crossing or a minus crossing, then the resulting topological relation being true about the invariant that you're working with just prolongs it, and you get that. Now, what about the other move, the rigid vertex move? That's important. So let's see what happens there. I have a node here, and I have a crossing here, and I have another crossing here. And we're examining j of this. And by definition, this is equal to j of, and now we keep everything the same and run this one over and multiply by a. And then we take the other guy and run this over, and this one under, and there, and multiply that by b. Okay, now look carefully at that. Here's a Reidemeister 2 move, and here's a Reidemeister 2 move. So I can simplify both of these because j is an invariant. So that means that I'm going to get A, J of this crossing, but the other part goes away, plus B times J of, and now it's the other crossing, and that part went away. And that's exactly J of the node. So you see, the rigidity of vertex means that when you put in the crossing, it's isotopic and it just flips out. And so we have invariance under the rigid vertex moves. And so we get invariance of rigid vertex graphs. This is really quite amusing, and you may wish to do some experiments with it yourself, trying different invariants. For example, let's look at an example of a rigid vertex graph and calculate an invariant of it. Well, suppose we were dealing with this one, all right? So then J, whatever would be of this, would be equal to A times J of, now I have to copy that and go this way. Plus B times J of, and I have to copy it and go the other way. And one of them, in this case, is an odd knot. This is equivalent to an odd knot. And this is a trefoil. And so you see that if J is sufficiently good invariant of knots and links to distinguish a trefoil, then it will distinguish this rigid vertex graph and tell you that the rigid vertex embedding is non-trivial, that there would be no way to undo this. It could even tell the difference between this and its mirror image if the invariant of knots and links is strong enough to tell the difference between the trefoil and its mirror image. So saying so and writing some other word, yeah. So this implies that this diagram here is non-trivial RVG and not equivalent to its mirror image. So we can do lots of things with RVG graphs and their invariants. Now, the Vasiliev example, the Vasiliev situation, which we were talking about, is an example of such a thing. You're told that you have an invariant, and you're told that the difference between that invariant on positive and negative crossings is exactly equal to the value on the node. So that this is the case in my theory where A is equal to 1 and B is equal to -1. And this turns out to be a very good choice for working on this kind of invariant because you can try to classify what kind of invariants you can build here. So let's take this as a given that we're going to be looking at invariants of this kind. And then another thing that people take on is I is said to be of finite type. N if I of some graph with greater than n nodes will always vanish. All right? So vanishes for G with greater than n nodes. Now, both of these conditions are due to Vasiliev. Vasiliev was thinking in a different way than I have been telling you so far. Vasiliev was thinking, let's look at the space of all possible embeddings of the knot. And then also include some singular embeddings. The singular embedding will, if you could then think of going through a path of embeddings. You could start with the trefoil, for example. You could start with a trefoil knot. You could go into a singular embedding continuously into a stratum where there was a singular embedding by making this closer and closer and closer until it touched. And then you could keep on going along the other side, past it, into a different isotopy class. So this is like there would be a wall, and in this wall we're in the trefoil class, and in this wall we're in the embeddings that are unknotted, and you can go through the wall and go through a singularity, and you would include these singular embeddings as well in your space of all embeddings. And then you would think big and try to understand the structure of the entire embedding space of all the knots this way. And then a difference equation is about functions on this space, which would have a difference when you went across a wall. And there would be functions that extended into the walls and so on. And he thought about cell structures for such spaces, and things cohomological come up in this context. And then it became natural in that context to think of the finite type. Now, what I want to show you is one thing, is the very first lemma of the Vasiliev theory, and then you'll see why I'm telling you this. If I is a Vasiliev invariant of type n, then I of G is independent of the embedding of G into 3 space for G with exactly n nodes. Now, to illustrate what this lemma means, let's suppose that n is equal to 2, and we're thinking about trying to calculate a Vasiliev invariant for this little knot that we were looking at before, and then you'll understand immediately what I'm talking about. So I wish to look at this. And I know, according to our rules, that I of this minus I of, and we'll switch a crossing, is equal to I of this. 2 nodes. And this is supposed to be of type 2. All that's fine, and then I could assume that I of the unknot is equal to 0, maybe just to make life easy, and I could assume that I of of somebody like this is also always going to be equal to 0 whenever that occurs. The reason why I would assume that is because you see that this would be equal to I of this over minus I of this under, right? And that's equal to 0. So you could, just for my sake of doing sample calculations, you could assume that on a little noded loop, 0, and it's going to be 0 on an unknot. And then this would have gone away, and we would be down to this. So now we want to keep on calculating. How can we find out about this? Well, so then we have the same Vassiliev formula that we had before. We have a positive crossing here, and the difference between that and the other one, switch that, will be I of the 3-noded guy. There's only one crossing left now. We're down to 3 nodes, huh? Ah, that's interesting. Because this is 0, because it's type 2. Right, I said n equals 2. So if I have a type 2 invariant, then a graph with 3 nodes vanishes, right? That was our assumption. But you see, that tells us that this and this, these two, have the same invariant. It didn't matter how you embedded the 2-noded graph. If you flip a crossing in the 2-noded graph, the difference is going to be 0, because with the difference is going to be the evaluation of a 3-noded graph. So the logic is very, very simple, and that's the proof of this lemma. I've just given you an example and told you the actual full proof of the lemma in the course of discussing my example, haven't I? So you see, this is very interesting because it means that these invariants bottom out on some graphical evaluations. And if we could find ways to evaluate graphs that would be harmonious with these Vassiliev invariants, well, then we could probably build them up from the graphical evaluations. So naturally, people started to think about that. Now, if I had more time and I was going to tell you about Vassiliev, I would tell you a little more, but let's look at the key theoretical point, which is what kind of restrictions are there in relation to, oh, I forgot what number I was on. Did I just, well, let's call it 9. I might be shifting up ahead, but it's, 9 exists. So I want 10. Okay. Right. Good. Now, so here is a beautiful way of thinking about this, which might be due to Ted Stanford in his thesis. I'll attribute it to him, but maybe it's other people as well. The idea is very simple. Suppose we're calculating a Vassiliev invariant, then we might consider a configuration like this. And we know that I of this is certainly equal to I of this. So this is going to produce an important relation if we start to analyze what's going on with it. Why are these equal? Well, because they're isotopic. By the rigid vertex graph move, you can pull this loop across and under and out, and then back over the top. Fine. So these are equal. And one way to get from under to over is by isotopy, by the isotopy invariance. You pull it in and push it back over. But another way to do it is to switch the crossings one by one. Switch this, switch that, and switch that. Now, what's that going to look like? Well, I think I have the technique here to do that fairly quickly. Let's see what we can do. Let's copy that. And then I'm going to stop writing the invariant. I'll just write the diagrams. And then here's another one. And I'm going to have this, but I want to switch the crossing. And then that will be equal to, that's positive here. So that will be equal to the noded one here. Node here. All right? So now I'm going to take this guy. Oops. And subtract the result of switching the next one and set it equal to the result of switching the next one. So I have to do a little work here. This one is the same. This one is going to get switched. And this one is going to get notified now. And this started out as a negative crossing, so this is the opposite signs, and so this will get a minus sign there. Now I'm going to do it again. If you don't mind, I will shift everybody up a little bit so that it'll all be on one slide. Yeah. So now I'm going to take this guy. And I'm going to do the same thing. Now you see that the result of doing what I'm doing is going to result in a summation which vanishes, because this with a minus, that with a plus, this with a minus, that with a plus, and so on, right? So we have that guy. We're going to have another guy here. And one more guy here. And let's see. Where are we? We did that. So now we're on this one. And this one is down. And it's going to get changed here to up and notified here. And this is going to be, this is minus, and this is negative again, so this will be negative. And then one more. That was this one that we're working on now. This is this one, which is positive, and this one becomes, oops, that's, there we go. Switch, difference. There we go. We're all set. Now look at what we have. All I did was switch this, switch this, switch this, switch this. So I started all down. I ended up all up. I add all this up, and I get the difference. This is canceling this, this is canceling this is canceling this, and this cancels this. So on the left-hand side, it just adds up to 0. On the right-hand side, oops, I have one more node to put in there. I have a 4-term relation about 2-noded embedded graphs. That is the embedded 4-term relation. That this minus this plus minus this plus this is equal to 0. So the way this is a fundamental relation about the evaluations that have to happen in a Vassiliev invariant. And now the amazing thing is what the consequence of this is for the case of the graphical evaluations. So in order to talk about that, I think I should rearrange this a little bit. But don't forget, all we did was we started with the Reidemeister moves and the notion that we're building Vassiliev invariants by difference equation, right? So now I'm going to assume that you remember all that and get rid of it. So we have the basic 4-term relation is this minus this minus this plus this. We'll fix it in a moment. Equals 0, right? So, well, already you see this is kind of like Dror's thing. You see, it's kind of analogous to it. And I don't know what to make of that analogy because the analogy is a little too vague, but I would like to because of the amazing structural relationship that this actually is implying, but you can't see that yet, but you will in a moment. You see we have 4 bits of curve here. And one way of diagramming the graph is to turn it into a chord diagram. Let me explain that for you here so that you see what I have in mind. Suppose, for example, that I was looking at this, just for the sake of that, right? And I want to describe the graph. So I start here at node 1, and then I get to node 2, and then I get to node 1, and then I get back to node 2. So as far as the graph is concerned, it goes like this: 1, 2, 1, 2. Just Gauss code, just like we talked about before, but now I'm looking at the Gauss code for the nodes. And then I could actually look at a Gauss code. I could write 1, 2, 1, 2. Like that. And so that means that whenever you see over here a node like this, then in the Gauss code situation, it's more like been pulled apart, and there is 1, 1, like that. Here it's just 1, but you pull it apart, and you get like a Gauss diagram. And then you can think about, well, what is it like for the Gauss diagrams? Well, you see there are there are 3 bits of Gauss diagram here. I'm going to tell you what it turns into. It turns into the following on Gauss diagrams. And if I show it to you, and then go back and talk about the picture, it will not be so strange. Now you have to compare. Look at this, and you see this touching is here, and the center one is the center one. Over here, you have the difference between these two. Let me use a little color. Over here, similarly. But just look at the first pair. This node is here. Now it's here. That's the same as these 2 nodes are in a certain order, and now they're in the reverse order. These 2 nodes are in a certain order, but with respect to a different line. Here they're in the order along this line. That's this line, mid. And then there's this line, mid. And here's this other line, northward. And here's the line northward. All right. And you see northward isn't participating in this one, but northward is participating in this one. In the other 2, northward has them in one order and then in a reversed order. So that's the situation. That's the pattern. You have the 3 arcs, and then you have the nodes that are happening. And the third arc, this is arc, call it A. You see, and A has a node that it's using, and this is A, and that's the node that goes in there. And that's the node that goes in there, and that's the node that goes in there, and that's the node that goes in there. So I've too much labeling, but you see that in the end, at the level of just the graphical diagrams, without worrying about over and under crossing, because at the level of n nodes, we only are asking what is the relation on the graphs. The relation on the graphs, written as a relation on the Gauss diagrams, is that you have chords like this minus the permuted version is equal to chords like this minus the permuted version. So our analysis of the Reidemeister moves takes us down to a restriction on the graphical evaluations that have to happen. And now, the amazing thing is that what you're looking at is that you walked from the Reidemeister moves into the basic patterns that are related to Lie algebras. Do you believe it? Let me tender persuasions. So let me remind you again what we had. That's what we had. Now, suppose that I think of diagrammatic matrices. So that means that I have a matrix T with indices I and j, and another matrix S with indices j and k, and I wish to write the product. Well, then that gives me then I arrive at the following formula. That is the sum on j of Tij S jk is equal to Ts in the ik position. That's the standard formula for multiplying matrices. Diagrammatically, that says that if I think of the matrix as a box with left and right indices, and I put the boxes together in a categorical way by connecting them like that, then this represents the product of the matrices, just so long as I sum over internal indices. Okay? So that's diagrammatic matrices. Theory of diagrammatic matrices. Now, what's a Lie algebra from the point of view of matrices? A Lie algebra is like this. You have a bunch of matrices, TA, basis. A runs from 1 to D. These are just names of the matrices, matrix names. Lower things are the indices for the matrix. And then we have that if I multiply TA times TB, and I subtract TB times TA, then there should be some constants, F, A, F, I, A, B, T, I. Oh, I got my indices backwards. I want a sum between upper and lower here because I do. So I'll label this constant, F upper A, B lower I, summed on I. And that where this is going to sum over the basis. In other words, the commutator of TA and TB belongs to the algebra generated by the TCs. Yeah? That's a Lie algebra in the matrix level. A Lie algebra is an algebra, linear algebra of matrices, which is closed under brackets. Of course, you can be fancier than this. But let's diagram this. So I wish to diagram TA, TB minus TB, TA equals constant, F, a bunch of constants. They're called the structure constants. Fi, Ti, summed on I. Oh, C. Let's use a C. Okay. If I want to diagram it, then I need somebody. Let me use this. A, B, C to mean F upper A, B lower C. Okay? You can't worry about that too much. It's not any more rigid vertex. It is the structure constant. And then what do we have? We have T, A, times T, B, minus TB times TA. But remember, I'm diagrammating, so I'll keep those indices in the same place and cross the lines. And we're summing on the internal index C, just as we did before. And there is our commutative relation. And I could abstract this. If I abstracted it, it would look like this. Oh. Fundamental difference of permutations, then being equal to a certain other graphical entity here. Huh. But the left-hand side looks like the kind of difference that we were experiencing at the level of the graphs in the bottom basement of the Vassiliev invariant. So let's see what would happen if we were to impose Lie algebra matrices into those graphs. Well, then we would start with the first difference, which looked like this. And then if we were in this Lie algebra category, we could put in the structure constant, and it would become this. And now, just for fun, let's assume that this is invariant under cyclic permutation. Now, if you look at some standard Lie algebras, like the SL2 Lie algebra, the one involving the Pauli matrices, you'll see that that's true. And in other Lie algebras, it's not true, but you can then add extra structure into the situation to make the cyclic permutation idea work anyway. So we'll just assume that this is invariant under cyclic permutation. If it's invariant under cyclic permutation, we can behave like diagrammatic topologists as we wish. So we can push this way and say, well, that's equal to this, huh? Oh my. Do you see what's happening? Now we can expand it back by the identity. And it becomes a difference of permutations on the third line rather than on the first line, the middle line. And there's our four-term relation as a consequence of Lie algebra. So we have the Lie algebra implies the four-term relation. Now, the place where the four-term relation in Vassiliev invariance is related to cohomology and things like that is in Vassiliev's original theory. It isn't used very much by the combinatorial topologists. But I couldn't resist showing you how it gives rise to this interrelationship with other area of mathematics. It's an amazing line via diagrammatics, which started with the Reidemeister moves a few minutes ago, and goes through translation to find out what relations have to happen on our graph invariants, what has to happen. And then we find that the patterns of relationships of those graphs correspond to Lie algebra, to matrix Lie algebra. And it means that you can actually evaluate the graphs that way. I mean, it's not just up in the air. I should indicate the concreteness of that for you a little bit, just so you see what I'm talking about. If we started with um, a diagram like this, you see, if that was our Gauss diagram, and we said, oh, well, I want to put in some matrices, I could say, sure, go ahead, put in matrices. So you'll put a matrix in here, and you'll put a matrix in there, and you put a matrix in there, and you put a matrix in there. And now these were the matrix labels, and we're going to have to sum over them. And so we're going to have um, this product. We could think of starting the product here of T. So it's going to look like TA, TB, TA, TB, and then it's closed loop, so that'd be the trace of that. And we're going to be summing over A and B. And this is the evaluation of this graph, which was the evaluation of this graph. So the graphical evaluations end up being the same, end up being actualized by Lie algebra, decorating the lines of the graph. And the fact that that these satisfy the four-term relations for the Vassiliev invariance corresponds to the Reidemeister moves. So I say that this four-term relation in Lie algebras and Vassiliev invariance is somehow an analogous situation to the four-tube relation in the Khovanov homology. But the four-tube relation in the Khovanov homology isn't backed up into Lie algebras or backed up by a theory of this kind. I don't think it's been investigated that way very much, or maybe someone has, and I don't know. But in this case, people pushed it very hard, so they understood what algebra it really corresponds to. And so I couldn't resist telling you a bit about that. Now, we are, that was a digression, but I hope you found it an interesting one. I'm telling it to you because this is how I try to think about things. I try to think about things by making comparisons like this. And this one has been on my mind, so I thought I would tell you about it. And it's also an excuse to show you these beautiful ideas related to Vassiliev invariance. So let's shift now and spend some time talking about what I promised I would talk about today. I actually have one more digression. It's more in the line of a bit of problem solving. Let me do it. It'll take 5 minutes, the way I have it in mind. This is a digression on the affine index polynomial, which we've been working with. And if I tell you this, maybe I can give you some interesting problems as well related to that. Remember how we did the affine index polynomial? I want to recall it for you, so let's just go and look at it for some case. Yeah. So we might want to calculate the affine index polynomial for this knot here, and we're going to find out it gives us a non-trivial result. And how do we do it? Well, we do it by calculating weights on a, oh, that was, I'm schizophrenic today about my non-classical crossings. This is now a virtual knot, right? Okay. We make a flat version of the virtual knot, and we make the indexing on the virtual knot. By the way, it's a good exercise to show that when you do this indexing, remember how we do it down if it's to the left and up it's to the right. It went down to -1, then it went back to 0, goes through the virtual crossing without change, goes up to 1 here, goes back down to 0 here, and we're done with the labeling. Let the crossings be A and B. Then you write down the weights. And the weights are obtained by looking at the difference here, that's the W plus, and looking at the difference here, and that's the W minus, remember. So doing it here again, I have -1, 0 minus 1, 0 minus 1 is -1, 0 minus -1 is +1. Up here, I have 1 and 0, and I have -1. And I'm sorry, yeah, -1, yes. So this guy is all plus, and the polynomial is by definition the sum over the crossings, the sine of the crossing multiplied by t to the w sub sine of crossing -1. So you take a w plus if it's a plus crossing and the w minus if it's a minus crossing, right? And so in this case, our polynomial is equal to, well, all plus, it's t inverse plus t minus 2. And that tells us that this is a non-trivial virtual knot, inequivalent to its mirror image in fact, and so on. But all the calculation comes from the flat diagram. So if we are dealing with flat virtuals, as we may well, then what is the story about the invariance of the weights for flat virtuals? And the answer is that that the weights of the flat diagram, and I will refer to the weights of the flat diagram as this chart, okay? Weights of D, the flat diagram, all right, is this chart. That's it, okay? So the weights of the flat diagram is equal to the weights of another flat diagram if D is equivalent to D prime by the third Rademacher move. Okay, that's easy enough for you to check. If you choose your labels of the crossings correctly, you'll see that no weights change. That's an exercise, if you like. Maybe that's part of our problem set. And then if you had a second Rademacher move, then let's see what would happen there. Suppose, let's find out. So it's flat, excuse me, flat. So then you have an A coming in here, and you have an A plus 1 coming in here, and then you go back to A, and here you have a B coming in, and it becomes B minus 1, and then it becomes B. So now let's look at the weight chart for this little piece. Okay, so we get, oh, I didn't give myself enough room. Oh, but let me just do it in our heads. B minus A minus 1 here, right? I'll make it large enough and rewrite it. Okay, so B minus A minus 1. And the negative 1 is A minus B plus 1. Now what about the other one? The positive weight is A plus 1 minus B. and the negative weight is B minus 1 minus A. So you see, these are the same, and these are the same. So the pattern is dot, dot, star, star. So, and without it, those weights don't occur at all. So you get two new weights, and they are like that, opposites to one another. That's what happens under a Reidemeister 2 move. And under a Reidemeister 1 move, you get 0 weights. So the 0 weights can be ignored. So we might as well ignore 0 weights. We'll just won't bother with them, okay? So then we have that the weight is invariant under the second Reidemeister move and under the third Reidemeister move, and under the second Reidemeister move it changes in this way. So I want to be as simple-minded as possible in this, and I want to state a result about invariance. So I can say the following, that if the weight of a diagram is invariant I'm sorry. I'd better get another slide and tell you this correctly. I see we're coming out of time on this, but we'll do this. This is this gives you something to think about, for which I'll make some problems related to. Okay. So I'm interested in the following question. Let me show you. I'll give you an example. Here's a nice example. Let's get the weights for this. Ooh. That's what happens when you're in a hurry. We'll just take it easy here. Let's do weights for this. 0. Minus 1. Minus 2. Minus 3. Minus 2. Minus 1. And 0. We're done. And let's call this crossing A, and this crossing B, and this crossing C. So I have 1, minus 1, 1, minus 1, and minus 2, 2, as you can check. For example, let's do C. 0, well, minus 2 going into 0, that's the plus 1, and it's a minus 2. And minus 1 minus minus 3 is 2. Yeah? So those are my weights. Now, here's a fact. If you're given D, and you let D reverse, let me make a better notation for it. dr, dr is equal to d with reversed orientation. Then the weight chart of d reversed is equal to the column reversal of the weight chart of d. That's another nice exercise, that if you reverse the arrow, try it on the example, reverse the arrow and compute this, and you'll find, oh, actually we proved it. I remember we proved it. I didn't state it this way, but we proved it. That is that the polynomial in T inverse is the evaluation for the reverse. But this is at the level of the charts, what's going on. You'll get a column reversal. So in this case, you would have the W plus would be minus minus 2, and the W minus would be 1, 1, 2, okay? Now, suppose, so let's see, let's make a notation so that we can say what we want to say. Let W hat of D be equal to the reversal of W of D, okay? So if this is W, I stop writing WT, W of D here, the D, then W hat would be minus 1, 2, okay? Now, if you do R3, then W of D not equal to W hat of D is preserved. Right? Definitely preserved, no problem, because it's the same, right? What if you do R2? And if W of D is not equal to W hat of D? Well, it still will be preserved, right? That is one way of explaining what it was that we found, because you see, what we found was that you would augment by n minus n minus n and n, right? That was what you would augment W with, right? So the property of being unequal to the hat is preserved under R2 because this because these two extra rows are symmetric under hat, and therefore there's no way that they can disturb the asymmetry of the rest. What's the conclusion? That if W of flat D is not equal to W hat of flat D, then D is not equivalent to D reverse. Because if it were, W of D would have to be equal to W of D reverse. And we're talking about up to Reidemeister moves, because the property of not being equal to the reversal is preserved under Reidemeister moves. So this is it takes a little elocution to state this result, but I think it's a very interesting result, because how else would you think about it? How else would you prove that a flat virtual diagram was inequivalent to its reverse. The polynomial isn't there anymore. You don't have the polynomial. But you do have the weights, and the weights are almost invariant under Reidemeister moves, except for this augmentation that we're talking about. So there's a flat invariant sitting in there, and among other things, that flat invariant lets you deduce in irreversibility. For example, in this case, we've deduced the irreversibility of this flat virtual knot diagram. So I was thinking about that this week along with those other thoughts, and I couldn't resist telling you about this. But we are out of time as far as going into the matter of how do you define virtual Kauffman homology, but that's what we're going to do all next time. We'll spend the whole period on virtual Kauffman homology. So I'll stop here. Questions? I intend, Andre, to compare this with your recent paper. I know you were thinking about flat invariants in relation to these kind of invariants, and so you may have had similar thoughts. If you have, let me know. I think it's there's a lot there in this interface between those polynomial invariants that we're playing with and what you can say about flat virtuals.
Okay. Should be nice.
Okay, I guess that's it for today.
Thank you very much.
Thank you.
Thank you.
Thank you very much.
See you next week.